Well, we all know that modern electronics is modern life is dominated by electronics, and if we examine electronics, we'll find that most of the systems that are there as part of electronics are digital in nature, and these digital systems are primarily based on complementary MOS technology. And if we want to understand the CMOS technology, at the heart of CMOS technology, or the simplest representative of CMOS technology, is this CMOS inverter. And CMOS inverter is what we is a digital, simplest digital gate. Basically, we all know that if you apply a logic high, then you get a 0, or if you apply a logic 0, then you get a logic 1 here. So that's the basic functionality of the this inverter that is there here. And so to understand why this CMOS inverter is so common and what's so special about it, there are different ways of looking at it. And some of these things you could find a detailed discussion of CMOS inverter, its characteristics, all of that you can find at this particular site here. And so today what we are going to do is look at CMOS inverter from a slightly different angle, which may help you appreciate why this circuit is so dominant, is so commonly used. And to do that, what we'll do is let's start from the simplest inverter that we can form here. So the simplest inverter, if I use an Nmos transistor, that I can form is if I just take a resistor here and we connect it to VDD here and RD here. So that's the simplest inverter that we can form using Nmos here. Using Nmos transistor, that's the simplest inverter that we can form. And it's obvious that if we apply input which is equal to 0 here, 0 volt, input is equal to 0 volt, the Nmos, the transistor will be off. The Nmos will be off. Off in the sense that the current through it will be extremely small. Note that if we plot the characteristics of an Nmos, many times we plot the characteristics of an Nmos like this here. We plot it IDS. Let's say this is the drain current IDS versus VGS. So we have a characteristics which goes like this here. Right, depending on now, of course, the nature of the curve will depend on whether the transistor is biased in linear or saturation region. And somewhere around here is what we call as the threshold voltage here. So below threshold voltage, the current is not 0, but it is small. And to see the full characteristics of a MOS transistor, one should plot it not on the linear scale, but one should plot it on the semi-log scale here. So this, if you plot, let's say, log ID, and you plot VGS here, then the graph that you would see is, let's say this is, let's say around VT here or so, the graph that you would see maybe like this here, right? So below VT, we see that there is current flowing below VT here. But as we go, as we go towards 0 or so, that's where the transistor is biased when we apply V in equal to 0. The current here is usually pretty small. How small and all that depends on what kind of a technology that we use here. And when we apply 0 volt here, so what we are saying is that the transistor is practically in the off state, very low current is flowing here. And if there's very low current flowing here, then obviously the drop across RD is negligible, and the output voltage we get is equal to VDD here. Right, so that's perfect. We apply 0 volt and we get an output voltage which is equal to VDD. So that's a perfect result. That's what we want. You apply a low voltage and you get high, and the maximum high voltage that you can get is defined by the supply voltage here, which is VDD here. Let's look at the second part here. Right, so let's look at the second part, the other part here, which is let's apply the voltage which is high here. So voltage, it is high here, so the highest voltage that we'll apply is VDD here. And this VDD is of course larger than threshold voltage here. So the transistor is in the on state. The transistor is in the on state, and a current obviously flows here now. A current flows in the on state, and the current flows here. Now in this case, note that the output voltage, we would like it to be low, and we would like it to be as low as possible. And so if we look at the transistor, let me draw the transistor's characteristics. ID, now I'm plotting ID versus VDS. And so for let's say gate voltage of VDD, so the characteristics would look like this here. This is for VGS equal to VDD here. Right, so this is for a fixed VGS. The characteristics ID versus VDS, we call this the output characteristics, looks like this here. Now we want the output voltage to be as small as possible here. So when we apply an input which is high, we want the output to be as small as possible, and ideally we would like it to be here, right here, which is we would like it to be V0 equal to 0 here. But note that V0 equal to 0, this implies that ID equal to 0. That current flowing is equal to 0. But if we look at this particular circuit here, we can see that the current is equal to, I will be equal to VDD minus V0 by RD. Right, that's the Ohm's law from here to here. The current will be VDD minus V0 by RD, and thus will be equal to, almost equal to VDD by RD. Right, because V0 is very small. So if we want this current, let's put this ID, if we want this current to be very small, if we want this current to go to 0, so that the output voltage here is pretty small here, the output voltage at this point is pretty small here, then what we want is this RD should be very high. RD should go to infinity. So what it says is that you should choose, in order to get an output voltage which is low and very close to 0, what you should do is you should choose RD which goes to infinity here, right? So RD should tend to infinity. So, or under practical cases, what we should do is we should choose RD that is much larger than the resistance associated with the Nmos transistor here, right? So we should do that, and that's also required because note that the power dissipation will be equal to VDD into ID, because that's the power that is coming from the supply here, VDD into ID. And if we want this power dissipation to be very small, we again want ID to go to 0 here. Sorry, ID to go to not to infinity, go to 0 here. So which again implies that you should choose RD which tends to infinity here. So what it tells us is that if we look at this very simple inverter, then if we want this inverter to behave properly, then especially when we apply an input which is high, then if we want a very low value of output voltage, we should choose RD which is very high, going towards infinity, and that would also keep the power dissipation which is very low here. But that's only part of the story. The other part is, well, the inverter not only has to behave functionally correct in the sense of low input voltage giving rise to high output voltage, and high input voltage giving rise to low input voltage. The inverter, the input to the inverter is dynamic in nature. The input is being switched and the output has to follow the input. So the delay is also very important. And if we look at that particular aspect, so let's draw this inverter here. Let's draw this inverter here, and this VDD here. So note that an inverter will not be used alone. So an inverter would be connected to another inverter, or an inverter may be connected to some input of a let's say an OR gate and things like that. So the inverter would be connected to something here. So let's say it is connected to another inverter here. Another inverter here, right? So it's connected here. Now the reason why we are saying this is that if we look at what happens at this particular node here, at this node here, so when you connect another inverter or another gate, there is a capacitance between here and here, the gate to source capacitance. There's a capacitance between here and here, the gate to drain capacitance. Not only that, if we look at this particular node, there's a capacitance between here and here, gate to drain, and we are not shown a body terminal. Body terminal is ground, so there's a capacitance which is connected from here to here, right? So what we find is that there is a net capacitance at this particular node here. So what I'm going to do is, just to simplify, I'm going to remove all of this and remove all this here, and just for simplicity, what we'll say is that to make the circuit more realistic, that there is a net capacitance connected at this particular node here, right? Some C total. So there's a capacitance connected to at this particular node, and what we are saying is that the input will be switching. So for example, let's look at a consideration. Suppose I have initially high, and then I switch the input to low here, right? So it goes from VDD to 0 here. So now what needs to happen is that if we look at the output is initially 0, the output is initially 0, and it has to go towards the VDD here, right? So when we go from VDD to 0, the output will go from initially very low voltage, let's say 0, to VDD here. But then what needs to happen is that this capacitor is initially, let's say, uncharged. Now it has to charge towards VDD here, and it has to charge through RD here. So it will go like this here, right? It will go start from 0 and go towards VDD here. And there is a delay here, right? There is a delay here. And this delay is very important. We want our circuits to operate at very high frequencies or as fast as possible here. So this delay tau is important, and we would like to keep this delay as small as possible, right? Delay as a small, and delay is nothing but, as you can see here, is related to, or at least proportional to, RD times CT here. So to keep the delay small, note that CT is fixed. So what we should do is we should make RD as small as possible. So RD should go towards 0, right? So that now causes a problem. We saw earlier that to keep V0 close to 0 and power dissipation close to 0, we want RD should go to infinity. And now we are just seeing for delay requires that we should make RD which goes to 0 here. So we have conflicting demand on RD. From one consideration from here, we want RD to go to very large values. And from the consideration of delay, we want RD to go to very small values, right? And this is a conflict that is there in this simple inverter. And as a result of which, one is not able to build a good inverter where we have just an Nmos and a resistor RD that is there here. And that's where the beauty of the CMOS inverter comes in. So note the CMOS inverters. Let's draw and let's see how the CMOS inverter satisfies this constraint here. So we put a PMOS here, and we connect it here, right? And so let's look at the first situation here. Let's look at this one here. So it says when you apply a high voltage here, so when you apply VDD here, this is the substitute for RD. So when you apply high voltage here, VDD, the PMOS is off. And therefore its resistance is very high. Resistance is almost infinite. So it satisfies this criteria. It allows us to get V0 equal to 0 and power also equal to 0 here. So that criteria is satisfied. On the other hand, now suppose we do the following. We go from VDD to 0 here. When we go from VDD to 0 here, so the moment we go to 0 here, the PMOS turns on. And it provides a low resistance path. And if there is a capacitor here, then the capacitor is charged through the PMOS here. It's a low resistance path here. So through use of a PMOS transistor, we are able to realize both of these objectives here. That when the input is high, we want the load of this NMOS transistor to be very high, and that happens because PMOS goes into an off state. And during switching, we can see here that during switching, when we go from VDD to 0, then the PMOS switches on and provides a low resistance path, and therefore RD times CT here becomes low, and there is a fast switching here. So the PMOS then satisfies these requirements from the point of view of keeping power dissipation low and also delay to a very low values. So it provides that particular characteristics. In one condition, PMOS being off state offers a very high resistance, while, while in the other case the PMOS offers a very low resistance here. And if we did not use PMOS, if we use a fixed resistance, then it can be either high or it can be either low, and therefore it would not satisfy both the requirements. Right? So that is what makes the CMOS inverter almost like a perfect inverter that is there here. Okay, and as we said, if you wish to know more about CMOS inverter, learn more about it, then this particular site is there where there's detailed discussion about the CMOS inverter and various aspects of it. Okay, so let's stop